In Chapter 1, we're going to be talking about ordinary differential equations. In fact, almost the entire chapter will only talk about the simple first-order single differential equation u prime equals f of t and u. This is not as restrictive as it sounds, because all the methods that we'll find for solving this problem will also work for the systems problem, that is, where u and f are vectors but not t. In other words, u is a vector of several functions, f is several functions, t is still a scalar. Basically, all you have to do is remember that u is a vector and f is a vector, and all the methods generalize immediately. Going from a single first-order equation to a system of first-order equations is really trivial. And furthermore, second-order and higher-order equations can always be reduced to first-order systems. In fact, most software for solving differential equations problems assumes you've already done that, and therefore is written for systems of first-order equations. If you have a second-order problem, you reduce it by the standard technique, defining v to be the first derivative, and then the derivative of v will be the second derivative. So you can reduce a second-order equation to a system of two first-order equations. A third-order equation can be reduced to a system of three first-order equations, and so forth. So solving this simple-looking equation is more general than it seems. The first and simplest method we're going to talk about is probably familiar up to all of you. It's Euler's method. All you do there is you approximate the derivative of u by u of t plus h minus u of t over h. After all, the definition of u prime is the limit of that as h goes to 0. So in numerical analysis, you simply take h to be small and hope that that's a good approximation to u prime. And then, of course, you solve this for u of t plus h and iterate with this. Extremely simple to program. For example, for this first-order nonlinear equation here, u prime equals 2t times 1 plus u squared. That's all you have to do to program it. The new u each step is the old u plus h times alpha of t and h, which in this case happens to be 2t times 1 plus u squared. You increment t by h, and here we are taking step size of 0.02. We're taking 25 steps of 0.02, thus out to 0.5. It gives an error of 0.01. Then we tried cutting h by a factor of 1, a factor of 2, so we decreased h to 0.01 and took 50 steps. Then the error was half, almost exactly half of what it was the previous step, so it appears to not only be converging, but the error seems to be proportional to h. Now, what we'd like to do here is what we do normally in other branches of numerical analysis, that is, simply get a formula for the error in terms of h. It turns out that that's much more difficult than it sounds. Actually, we'll do that later on, but it's not nearly so easy as it sounds. In other words, what we're really interested in is the error at a fixed t. Like in the last example, we looked at the error at t equals 0.5 with different step sizes, and we saw that the error went down by approximately a factor of 2 when h went down by a factor of 2. So it looks like it's converging, but we'd like to get some kind of theoretical error bound on the error itself. Well, as I said, that's not easy to do. So we start out by defining something else that seems to be related to the error, but it's not immediately obvious how it's related to the error. It's going to be something called the truncation error, and it's going to be a lot easier to calculate than the actual error. How it's related to error will be a subject of investigation here. But we define the truncation error to be the amount by which the solution of the differential equation fails to satisfy the approximate finite difference equation. In this text, we'll consistently use small u to represent the exact solution of the differential equation, and capital U will be the approximate solution, which of course will only be defined at discrete values of t. So it seems like a reasonable measure of error in some sense. If the approximate solution is close to the true solution, you would expect that the true solution would nearly satisfy the approximate equation, and the approximate solution would nearly satisfy the exact equation. The latter is not possible because the approximate solution doesn't have a derivative, so you can't take the approximate solution, which is only defined as discrete points, plug it into the exact differential equation. So we do the opposite. We take the solution of the differential equation, little u, plug it into the approximate equation, and hopefully that should nearly satisfy the approximate equation. And the truncation error is a measure of how close it comes to satisfying the approximate equation. In other words, the truncation error is the residual that occurs when you take the exact solution, little u, of the differential equation, plug it into the approximate finite difference equation, and that's called the truncation error. How it's related to the error is not clear, but it seems like it ought to be small if it's a good approximation to the differential equation. In fact, we say that a finite difference method is consistent with the differential equation if the truncation error goes to 0 as the step size goes to 0. In other words, the finite difference equation is consistent if the truncation error is of order at least h. Now that sounds like it might be difficult to plug in the exact solution into the approximate equation since you don't know the exact solution, but it's not. Here's the truncation error for the Euler method. We simply take little u. Remember, little u is defined as the solution of u prime equals f of t and u. Plug that into the Euler equation, and here's the residual. And the technique is always we expand everything in a Taylor series around t. So first we use the fact that little u is the exact solution of the differential equation to say that f of t, u of t, is equal to u prime of t. Then we expand u of t plus h in a Taylor series around t and subtract u divided by h, and it all comes out to be 1/2 h u double prime. So we see that the truncation error for Euler's method is order h, proportional to h, which is not surprising because we noticed that the error experimentally seemed to be proportional to h, so there does seem to be an association between truncation error and error. In this case, at least, they're both of order h. By the way, there was a little phrase in the definition of truncation error. It said it was the error that results when you plug in the exact solution into the finite difference equation in normalized form. Well, what does normalized form mean? Well, this is Euler's equation in normalized form. The problem is we could always multiply Euler's equation through by h to the 100th power and then plug in u, and of course we get a truncation error of order 101, I guess. That's not fair. It has to be normalized. That means such that the left-hand side approximates u prime and the right-hand side approximates f. So this is normalized form. If I multiply by h or 10, it's no longer normalized. Okay, well, we suspect that the truncation error and the error are related. Truncation error is it's not clear how it's related to error, but it's easy to calculate, and it ought to be small if it's a good method. Unfortunately, it's not the case that consistency automatically guarantees convergence, and we give an example here. In this method here, another finite difference method where we've basically approximated u prime by another approximation, which is actually much more accurate than Euler approximation. In fact, the left-hand side of this equation 121 actually for small h does approximate u prime much more accurately than u of t plus h minus u of t over h. So you would expect that this would be a very good, would be more accurate approximation than Euler's method. And so we try it, and basically we solve this for u of t plus h in terms of u of t, ut minus h, ut minus 2h here. Now, this is a multi-step method, unlike Euler's method, where u of t plus h depends only on u of t. For this method, it depends on u of t minus h, u of t minus 2h. In other words, last three steps. That means that you can't just start from the initial condition. You have to use some other method to take the first two steps before you can use this method. You need a starter method. For example, you could use Euler's method to take the first two steps and then switch to this. It's a third order recurrence relation, so you have to have three starting values. For this example, I simply took the exact solution of the differential equation that I'm going to solve, same differential equation as before, u prime equals 2t 1 plus u squared, u of 0 equals 0. Same differential equation as we solved using Euler's method. So I just took the exact solution. I kind of cheated to take the first 3 steps and then switched over to this multi-step method. And the results are on the next page, and they're quite surprising and disappointing. In fact, I forgot to mention the truncation error for this method is actually proportional to h cubed. In other words, if you take the exact solution of u prime equals alpha of t and u and plug it into that the finite difference method we're using now and calculate the residual in normalized form, it comes out to be, after expanding in everything in Taylor series, h cubed times something. So in fact, it's not only consistent, but it's higher order truncation error than Euler's method, and yet the results are terrible. We try h equal to 0.02, same as we did with Euler's method, take 25 steps of h equal to 0.02, exact starting value as I said, and it's actually doing quite well at the beginning, and then error starts to grow until by the time we get 0.5 the error is several hundred%. So maybe we just need to make h smaller. No, if you cut h in half, results are actually much worse. In fact, it overflows before it even gets to 0.5. So it's clear that this method is totally worthless in spite of the fact that it's consistent and it has a high order truncation error. So the question becomes, what is the relationship between truncation error and error? Well, the method we just saw, in spite of being consistent with differential equation and higher order truncation error, in other words, more consistent than Euler's method, it's totally unstable. The error grows exponentially. The method is totally useless. The smaller h is, the worse the results are. Well, we're going to define stability as follows. An approximate finite difference method is stable if the error goes to 0 as the truncation error goes to 0. Well, by this definition, trivially, it's clear that if a method is consistent and stable, it converges, because consistency means that the truncation error goes to 0 as h goes to 0, and stability means that the error goes to 0 as the truncation error goes to 0. So trivially, if a method is consistent and stable, the error goes to 0 as h goes to 0, which is what we want. It's convergent. So stability plus consistency equals convergence. But that doesn't tell us anything about how to determine if a method is stable or not. So that's what we want to look at in the next section. How do you know whether a method is stable or not? Well, let's talk about general multi-step methods. The Euler's method and the unstable method we looked at are both special cases of this finite difference equation, and many of the other methods that we'll see in this chapter are also special cases, not all. This is a multi-step method. The left-hand side is supposed to approximate u prime. It's a linear combination of u at different values. The right-hand side is supposed to approximate alpha of t u. It's a linear combination of alpha at several different points. So the alphas are coefficients of the u's, the betas are coefficients of the alpha. So Euler's method, for example, beta 1 would be 1, the other betas would be 0. In fact, the unstable method also. And Euler's method, alpha 1 would be -1, and the other alphas are 0, for example. So how can you tell whether a multi-step method is stable or not? Consistency, truncation error is relatively easy to calculate. You just take the exact solution, little u, plug it in to both sides of this equation and see how different they are. And it may be complicated because you'll have to expand several things, maybe in Taylor series, but it's straightforward to calculate the truncation error, so it's easy to tell if your method's consistent or not. And basically, unless you've just done something dumb, it's going to be consistent. So consistency is easy, but stability is not obvious. How do we tell if a method is stable or not? Well, it turns out that it's actually pretty easy to determine stability. And there's a theorem in this chapter. The proof is rather difficult, but we'll just state the theorem. that says basically you look at the left-hand side of your multi-step method, the side with the alphas on it, and there's a characteristic equation associated with that in a trivial way here. Alpha 1 through alpha m is an mth order characteristic polynomial. The roots of that characteristic polynomial determine whether the method is stable or not. And what the theorem says is that if all the roots, all m roots of this characteristic polynomial are less than or equal to 1 in absolute value, and all multiple roots are strictly less than 1 in absolute value, then the method is stable. In fact, we get an error bound that says that the error at a fixed point tk is less than some constant times the truncation error, times some constants, plus the maximum of the starter errors. In other words, a multi-step method, remember, you have to take the first few steps with some other method, and of course how accurate those are determines the overall accuracy. Those have to also be going to 0 with h, so you have to use a consistent method to start the multi-step method so that the first few errors are small, but assuming those are going to 0 and the truncation error is going to 0, in other words it's stable, it's consistent, then the method converges. So basically we see here that if the method is stable, which means that the roots of that characteristic polynomial satisfy the root condition, which by definition is that all roots are less than or equal to 1 and any multiple roots have to be strictly less than 1. We refer to that as a root condition, so we don't have to say all that out every time. So if all the roots satisfy the root condition, then we have that the error at a fixed point is bounded by the truncation error plus the initial errors, which depends on the other method used to start it. So that's what we would like. That's kind of what we suspected, that as long as the method is stable, the error goes to 0 as fast as the truncation error, assuming your initial starter method is good, is compatibly accurate. So the error and truncation error are in fact related if the method is stable. If the method's not stable, just don't use it. It's no good, whatever. Okay, so the proof of this theorem is rather complicated. However, it's possible to prove the converse fairly easily. That is, I'm going to show you now that if the root condition is not satisfied, we'll see why the multi-step method is totally useless, unstable. Okay, to show that multi-step method is unstable and totally useless if the root condition is not satisfied, here's the general multi-step method again. Alpha's on the left-hand side, betas on the right-hand side. Notice the stability criterion has nothing to do with the betas. The betas don't influence stability, only the alphas do. And it's the characteristic polynomial lambda to the m plus alpha 1 lambda m minus 1 plus alpha 2 lambda m minus 2 and so forth down to alpha m. That's the characteristic polynomial. It's just you can write it down immediately from looking at the left-hand side. We're going to show that if the roots do not satisfy the root condition, it's unstable. And we do that by simply looking at the simplest possible differential equation and show that the method's no good even for that. U prime equals 0. In other words, just take f to be the identically 0 function and u of 0 equals 0 starting point. Then in that case, f is identically 0 and all you get is this equation, and this is simply a homogeneous constant coefficient linear recurrence relation. And from discrete math, we know that those have solutions of the form lambda to the k. So we plug in u of t equals lambda to the k in this to see what values of lambda will give us a solution. And we get exactly the characteristic equation after dividing by the lowest term. So here's the characteristic polynomial, and the roots of that, we're looking for solutions of the form lambda to the k. So what are the roots of that? Well, if there are m distinct roots, then the general solution of this linear recurrence relation is all linear combinations of lambda 1 to the k, lambda 2 to the k, and so forth. In other words, if lambda 1 is one root of the characteristic polynomial, lambda 1 to the k is a solution, lambda 2 to the k is another solution, any linear combination solution, because it's a constant coefficient, it's a homogeneous linear recurrence relation. So this is like the general solution. Now, it's true that if you plug in if you start out with your first m steps all exactly 0, all the a's are going to be 0 and you're going to get the exact solution. But if you change any one of those starting values the tiniest bit, machine precision, then what's going to happen? Then the a's will not all be 0 exactly. They may be close to 0, but not exactly. And the solution blows up as h goes to 0 because remember that k is just tk over h. So basically the solution is lambda 1 to the tk over h, etc. If any one of these roots is greater than 1 in absolute value, and they can be complex, but even if they're complex, we look at their absolute value, complex absolute value. If any of those have an absolute value greater than 1, then you've got something bigger than 1 to the tk over h power. As h goes to 0, that goes to infinity. So we're solving the simplest possible equation, u prime equals 0 with u of 0 equals to 0. The solution obviously is u equals to 0 for all t. As h goes to 0, your approximate solution actually blows up. It's extremely unstable. So that shows that all of the roots have to have absolute value less than or equal to 1. And in fact, if you have any double roots, if lambda is a double root, then it's also known from discrete math that k lambda to the k will be a solution, and that will blow up even if absolute value of lambda is equal to 1. So if you have double multiple roots, then the absolute value has to be strictly less than 1. So that's where the root condition comes from. Now remember our unstable method here. This is a multi-step method, and it's very consistent. Order truncation error is order h cubed. The characteristic polynomial would be 2 lambda cubed plus 3 lambda squared minus 6 lambda plus 1 equals 0, and the roots of that are shown here. One root is 1, as it always will be. 1 is 0.186, and 1 is minus 2.686, which is the cause of the instability. One root is bigger than 1 in absolute value. It's unstable. In fact, if you looked at the numerical results, you might have noticed that the error was actually increasing by a factor of about minus 2.7 every step. So we saw the exponential growth in the error. Okay, in the next section, we're going to talk about the Adams multi-step methods. These methods have all the left-hand side is just like Euler's equation, u of t plus 1, u of t k plus 1 minus u of tk over h. So they approximate u prime the same way as Euler does, but a more general right-hand side involving the betas. Now the Adams methods are automatically stable because the characteristic polynomial then is just lambda minus 1 equals 0, which has a root of 1, or lambda to the m minus lambda to the m minus 1, which has several roots of 0 and 1 of 1. Anyway, it's stable. So it's guaranteed stable. So the Adams methods, by the choice of the left-hand side, you don't have to worry about stability. All you have to worry about is consistency. So then it's just a question of choosing the betas to make it as high order truncation error as possible. So how do we find the betas? Well, if we knew the betas, we could calculate the truncation error the usual way. Just plug in the exact solution little u into the approximate equation and see what happens. Since we don't know the betas, well, in this example, we're going to take m equal to 2, so we've only got 3 betas on the right-hand side. And to calculate the optimal betas, what do? You just calculate the truncation error as if you knew the betas and carry it on out, and then see what betas need to be to make the error as high order as possible. So we plug in little u, which remember is defined by this as the solution of u prime equals f of t and u, into the approximate equation, and that means that f of tk plus 1, u of tk plus 1 is u prime of tk plus 1, and so forth. So we have this. Now this term and this one and that one have to be expanded in a Taylor series, and it's a bit involved here. But eventually we end up with the following. Again, if we knew what the betas were, we could simply plug them in and see what the truncation error is. We don't know the betas, so we simply say, well, we'd like for this term to be 0, And we'd like for as many of these terms to be 0 as possible. If this one's 0, then it's order h and it's consistent. If that one's also 0, then it's order h squared. If that one's also 0, it's order h cubed. Well, we've got 3 unknowns to play with, so we ought to be able to make all 3 of those 0, in which case the error would be order h cubed. So we simply solve the system of three equations for the 3 unknowns for beta 0, beta 1, beta 2, and here's the solution, and then the truncation error is order h cubed. So we don't have to worry about stability anymore. It's guaranteed that the error is the same order as the truncation error because it's stable, and so we just have to concentrate on choosing the betas to make it as high order truncation error as possible. Well, recall that this is the typical Adams method here. Now the beta 0 is an important parameter. If beta 0 is not 0, you see you have implicit method. In other words, you can't simply solve this for u tk plus 1 like you could with the Euler method and the unstable method in terms of utk and utk minus 1 and so forth, because there's a new u here, and this might be a nonlinear function. So there's a problem if beta 0 is not 0. It's an implicit method. It's actually possible to get around this fairly easily, but there are advantages to having beta 0 equal to 0 so that it's explicit. It's a little easier to use. So the Adams methods are divided into 2 families. One where beta 0 is 0, those are called the implicit or Adams-Moulton methods, Adams-Bashforth methods, and the implicit ones where beta 0 is not 0, those are called the Adams-Moulton methods. And as you might expect, if you force beta 0 to be 0, you don't get as higher order truncation error because you have one less parameter to play with. So the implicit methods with the same number of steps are one order truncation error more accurate. Here's the second order implicit method, third, fourth, and so forth. You could compile a table with a lot more. The explicit methods, here's the table for the explicit methods. And the beta 0s are all 0, which gives us one fewer parameter to play with, and therefore the a method with the same number of steps is one order h less accurate, but it's explicit. Now, people will often use the two together. It's called a predictor-corrector method. The predictor is the explicit Adams method. The corrector is the corresponding implicit Adams method. And what you can do is every time step you use the explicit method. Here's a, I believe it's 4th order explicit method to calculate u at tk plus 1, or at least one estimate of the new u at the new time step, and then you use the implicit method and you simply plug that in as an approximation to u of tk plus 1, because it's a very good approximation, 4th order approximation. So you basically use a predictor to predict the value of u at tk plus 1, then you plug that in on the right hand side, the beta 0 is not 0 here, and calculate a new one. And in theory you could iterate that until it converges, but one iteration turns out to be sufficient. So this is a typical predictor-corrector method. Here are some results when we applied it to the same problem as the other methods. U prime equals t squared times 1, u prime equals 2t times 1 plus u squared, u of 0 equals 0. And here, with the same step sizes as we used with the Euler's method, get much smaller errors at 0.5. Remember, with the Euler's method we also took 25 steps at 0.02. The error there was about, I believe, 0.01. Now it's 10 to the minus 6th. Cut h by a factor of 2. The error goes down by a factor of about 16, which is consistent with the 4th order method. And obviously it seems to be perfectly stable and converging very rapidly.